and welcome to this workshop on how to prepare your students for the Quebec Indigenous Science Fair. This is a self-training for teachers, and throughout this video you're going to learn how you can better prepare for your students depending on what kind of projects that they want to do, what are their main interests, and trying to give them some freedom, but at the same time make sure that their project is following the scientific method or the engineering design process so that we have some validity in the science that they're using, but they also are working on something that is of interest to them. So I'd like to introduce myself. I'll be your trainer for today. I'm Dominic Tremblay. I'm an Ontario certified teacher. I'm a Smarter Science trainer, and I'm also a Lego Education certified teacher trainer. And today we're going to be using a lot of the Smarter Science resources as they are very well designed to support students in creating a science fair project. You will see that many of these teaching strategies will be useful in your classroom, no matter whether you are preparing your students for the science fair, working on a science fair, or just to teach your Quebec science curriculum as well. The goal is that throughout the school year, you use these techniques with your curriculum so that when it's time to prepare the science fair project, it's not new for students. They already have an idea on how to use a scientific method or the engineering design process. So a lot of these pre-lessons could start right now at the beginning of the school year, and then when it's time to start a science fair project, for students, it won't be new. It will be something that they're familiar with, so it makes it a lot easier for the science fair project. So before we get started, I'd like to give you an overview of science fairs in Canada. So most science fair will start in a school. We do have some science fair also starting with homeschool students as well as clubs as well, science clubs. But most science fair will start in a school, so it starts at the school level. And as part of the Quebec Indigenous Science Fair, you will probably run a school science fair. If you only have a few projects, it may not be necessary to have a full school science fair. But if you have, a few projects, it'd be nice for them to showcase their project before they get selected to go to the regional science fairs. Now, in Canada, we have over 100 regional science fairs, and they comes in different variety. Some of them are regional based. Like if we take the Calgary Regional Science Fair, or the Vancouver Regional Science Fair, or the Toronto Science Fair, or even the Timmins Regional Science Fair. So we have them across Canada. These science fairs are defined by their regional boundaries. Now, we also have some language-based science fairs, and that, as an example, the English Montreal Science Fair would be a science fair that is language-based. Françaiscoise for French Saskatchewan would also be language-based. So it includes all the students that speak French in the province of Saskatchewan. So it's partly regional based, but it's mostly language based. We have many Acadian science fair also in Eastern Canada that would be language based. And then we also have cultural science fairs, mostly Indigenous science fair across Canada, Quebec Indigenous Science Fair being one of them. You will also see Manitoba Indigenous Science Fair. You will see many Indigenous Science Fair as well in Nova Scotia and in the Maritimes. So there's some Indigenous Science Fair across Canada. And students get to do science using traditional knowledge as well as a more Western scientific method. And by bringing the two together, they can produce very rich projects where they bring their culture, the culture that they inherited from their grandparents and their parents, and then they can use the scientific method to work on these projects. Now, in Quebec, there's also the Quebec Provincial Science Fair, which would include students from across Quebec. Now, the Quebec Indigenous Science Fair doesn't go through the Quebec Provincial Science Fair. So if your students from your school were selected for the Quebec Original Science Fair, if they get selected, they could go directly to Canada-wide Science Fair. So only the regional based science fair in Quebec would go to the Quebec Provincial Science Fair, which is quite an exception in Canada. In most other provinces, students will go directly from their regional science fair to the Canada-wide science fair. And from Canada-wide science fair, students could get selected for an international participation, including the Milset International Science Fair, the Intel International Science and Engineering Fair, called ISF, or even USIS. Keep in mind that students don't necessarily get selected at Canada-wide Science Fair for these events. Sometimes they get invited after the fact, or sometimes they need to, once they've done one Canada-wide Science Fair, they need to apply to participate in one of these international events. This is the case for the ISF, International Science Fair. So in all, this is what science fair looks like in Canada. I hope it gives you a great overview of what is available, and you see where your school science fair is starting, and that's extremely important for you to start with the school science fair to get students interested. And as you can see, the Canada-wide Science Fair has been everywhere across Canada. It started in 1962 in beautiful Ottawa, and it has visited every single provinces and some of the territories as well. Now, if you look at the recent year, you will see in the upper left corner that we now have a rotation of going from Ottawa to Fredericton to Edmonton, then to Ottawa, Fredericton, Edmonton. Now you will see that 2020 is missing. It was canceled because of COVID, and 2021 and 2022 were virtual science fair. For the first time in 2023, we will be back in person in Edmonton, and then that rotation between Ottawa, Fredericton, and Edmonton will continue. So hopefully you have some of your students that get selected for this great event. If they don't, just participating in the Quebec Indigenous Science Fair is a great experience for them to get to travel to a different part of Quebec that they may not have visited, and they get to see their peers and interact with their peers who also love science. So this is just a quick overview of what the Canada-wide Science Fair looks like in person. At the Canada-wide Science Fair, we do have a standardized display board that you see on this picture, which is not the case necessarily for regional science fair or even school science fair. For a school science fair, you could use your good old trifold cardboard display board. That would be perfect as well. And this is when we welcome all the participants coming from across Canada. So we will welcome students coming from a variety of regions, from a variety of cultural science fair and language-based science fair. This was in Fredericton, and we have a bunch of volunteers waiting for the buses coming from the airport to welcome the students. So it's a great experience for our students, and this is just an example of our Best in Fair from a few years ago, where we select our Platinum Award winner. And this is the experience with judging. Judging is part of the science fair. Hopefully you can organize it at your school science fair, just so that students already have some sort of experience presenting to a judge. It may be different for them. Maybe they've never done that. It's a little bit more formal. Keep in mind that most judges are not looking for a long presentation. They're not looking for a monologue. They're more looking for a conversation with your students. So hopefully when you have your school science fair, you can also train your judges to have a conversation rather than listen to a long monologue from the students. Now at the science fair, we have 3 age category. So we have junior, which would be for your secondary 1 and 2 or grades 7 and 8. We have intermediate for grade secondary 3 and 4. This would be grade 9 and 10. And then we have senior for secondary 5 and CEGEP, or that's also for grade 11 and grade 12. Now, keep in mind that at your school science fair, you could have students younger than that participating. And even at the Indigenous Science Fair, we welcome students who are younger in the age grade 5 and 6 category. They may not be selected for Canada-wide Science Fair, but they also have a great experience at the Indigenous Science Fair. So that's why many school science fair will even invite kindergarten, grade 1 and 2, grade 3 and 4, and even grade 5 and 6 to participate. So at your school science fair, you're free to do whatever you want, keeping in mind the age group that is allowed at the Quebec Indigenous Science Fair and then at the Canada-wide Science Fair. So this is an example of what we have with the younger students. Sometimes the younger students, instead of doing a project in pairs, the whole classroom will be presenting. And you could have in your school a celebration of science with students from all ages. You could have like kindergarten all the way to the end of high school, just to have like a full celebration of science, and then officially judging those students that are eligible to go to the Quebec Indigenous Science Fair and then the Canada-wide Science Fair. I did say pair. Usually projects are done in pairs, or they can be done alone. We will not allow at the Canada-wide Science Fair students working as a group of 3 or more. It has to be 1 or 2 students. So keep that in mind. If you have larger teams, they will not be allowed to continue the competition. But they can still present at your school science fair and have lots of fun. So at the science fair, we actually have 3 types of projects. We have the experimental design, we have the innovation and invention, and then we have the study and research. And actually recently, very recently, the study and research has been merged with experimental design. So if we look at the 3 types of projects, experimental design is when the students will do an investigation with a hypothesis and using the experimental method to test the hypothesis. There needs to be at least 1 independent variable and 1 dependent variables that students will be measuring. And you need a bunch of control variables to make sure that the experiment is valid. And we're going to spend a lot of time a bit later in this training seeing how we can get students to come up with these variables. Then we have the second type, which is innovation and invention. This is when your students would be creating something new. If they come up with a new device, a new model, or sometimes they will actually be improving something that already exists. As an example, your students could be interested in working on dog sleigh and seeing how they can improve the skis on dog sleigh. Or they could improve the structure of an igloo. That would also be an innovation and invention, because they're actually modifying a device or a technique or a structure that already exists. Most innovation and invention are not something 100% brand new. It builds on something. The same way as all the big companies creating like phones and shoes and cars, they don't start from scratch. They look at what's already existing and they bring innovation. So it's okay to start with something that already exists and bring up those new invention. Okay. And then there's the study and research. In the study and research, it's a little bit different than experimental design, but it's also very similar at the same way. In a study or research, students will still be collecting data. They will still be analyzing and seeing trends in data. The only main difference is in an experimental design, students will voluntarily change a variable. Whereas in a study, students could, let's say, look at water quality, looking at in different communities. So looking at the rivers that are feeding and providing water to the different communities, and they could be doing water quality tests on all of these. So they're researching, they're not actually changing something voluntarily. It's not like, oh, I'm going to see the effect of this on this. So they're collecting data. If they're observing animals in their environment and they're collecting data, they're not trying as a scientist, as a young scientist, they're not trying to change something, but they're trying to collect data, maybe compare, they may be contrasting, they may be analyzing the data, they may be seeing some trends, building some bar graphs and line graphs and trying to see if it's linear, seeing all the trends. So that would be a study as well. So study will often use either data that is collected through observation and measurement, or it could also be data that has been collected by someone else. So it would be okay to do a research project where students will use data coming from StatCan or coming from Environment Canada. So it's okay to go and use data that has been used by someone else, but to analyze it and come up with some of the trends that you see in the data. So let's practice here. We have 3 science fair projects, and I want you to tell me if they are an experimental design, a study, or if they are an innovation. So let's have a look at the one. Which distraction would significantly affect your reaction time? Listening to music, responding to questions, or texting? My project investigated the effect of different distractions on the reaction time of junior and high school students. Your safety matters. For a quick reaction time while walking across the street or driving down the road, try putting your phone down and sending that text later. So that students was working on distracted driving, looking at texting, listening to music, that kind of thing. I'm going to read the second one before I give you the answer. So the second one is, my project is about the Mi'kmaq traditional medicines. The Mi'kmaq people mainly use the 4 sacred medicines: sage, cedar, tobacco, and sweetgrass. Each medicine has its own purpose in our culture, and I'm very happy to be given the opportunity to educate others on the 4 sacred medicines of the Mi'kmaq people. So that's the second project. The last project from Quebec, vertical farming is agriculture in urban buildings instead of rural fields. This will allow more produce to be grown in less space using much less water and reduces greenhouse gas emissions. My project involved the construction of a working model vertical farm that incorporates features such as hydroponics, aquaponics, and the use of renewable energy sources. So, I want you to pause this workshop right now and try to find out, maybe by discussing with your peers, your colleagues, what kind of projects all 3 of these are. I'm going to give you a hint. There's one of each. So all of the 3 types that we just saw, there's one of each. So I hope you had a good discussion here, trying to find what kind of project they were. So let's have a look at what they actually are. So the first one on the left, the distracted driving one, is actually an experiment. This girl did an experiment. Didn't use an actual car, but use a video game. So she was trying to distract the driver with different types of distractions and seeing how this would affect their reaction time. So it was an experiment that was a variable that was the type of distraction. So that was the independent variable, and the dependent variable was the time, so the reaction time. And obviously she tried to control everything else. So that's an experiment on the left-hand side. In the middle, this student did not perform an experiment. He collected data, probably by doing interviews, by doing surveys, by finding books about the 4 sacred medicines. So when you try to collect data this way, that becomes a study. Just keep in mind that the study recently has been merged at Canada-wide Science Fair to be merged with experiment. The last one, when you're building something, you're building a model here, you're working on an invention and innovation. And even though vertical farming does exist, the fact that this student is trying to build and trying to improve the system, that becomes an invention and innovation. Okay, let's practice some more. I have 3 more projects. Now you have a little bit more experience. So let's have a look at these 3 types of projects. So diabetes affects 246 million people worldwide, and its incidence rate is projected to increase. Early diagnosis and management of prediabetics and diabetics is of paramount importance to healthcare system. We developed a non-invasive glucose biosensor capable of discerning between normal, pre-diabetic, and diabetic subjects that can be implemented for large-scale screening of populations at low cost with minimal technical skill to administer. So they created this device, a non-invasive glucose biosensor device. So the second one, using a homemade launcher of my own design, the gravity-assisted ballistapult, I threw objects of different masses and shapes 3 times, each at different launch angles, then recorded and analyzed the results. I then improved the ballistapult and test process to conduct a second round of testing to find more comprehensive results. So this is like similar to a catapult. And then by changing the angle, she was trying to see how far each of these balls would go. And the last one, after reading an article in Popular Science, I was inspired to grow kombucha fiber. I then compared it to cotton, polyester, ox leather, and vegan leather for dyeability, durability, and strength. I determined that kombucha fiber is stronger and more durable than cotton, polyester, technofiber, and vegan leather. Only ox leather fared better than kombucha in durability and strength. So I'm going to give you sometimes, I encourage you to pause the workshop at this point, have a discussion with your peers, other teachers. What type of projects do we have here? So I assume that you're back. So if we look at the different type of projects, the first one, they created a sensor. That's definitely an invention. That's so clear. The second one, we could think that it's invention and innovation because the students is working on the ballistapult. However, the focus was more on the angle at which you were launching it and then the distance that it would go. So it was an experiment because you had an independent variable, which was the angle at which it was launched, and then the distance that it would cover, that was the dependent variable. We definitely have an experiment here. Now, when we look at the last one, we could think that it's a study because she did read an article in Popular Science, but she actually tested it. So she tried to create that fiber and test it. So that would be, even though she got inspired by a magazine, that would fall into the innovation and invention category. So those are the different types of projects. Now I have something else for you. We also have the different challenges. And challenges are kind of big, broad topics that we have at Canada Wide Science Fair. Now, keep in mind that these also change from time to time. So this is the one that we have in 2022. But keep in mind that you need to have a look as sometimes new challenges get added. You need to make sure that you look at the most recent list. But in 2022, these are the challenges that are available. First one is agriculture, fisheries, and food. So this is a broad category that would involve feeding the world. The second one is very general. It's called curiosity and ingenuity. That's usually the categories that will cover anything that is not covered in the other categories. It's kind of the others. The third one is digital technology. And this has to do with anything that would be digital. Coding, computer science, robotics would go under digital technology. Creating website and database and analyzing data using computer and creating a mobile app on a cell phone would all go under digital technology. Then you have disease and illness, which if you look a little bit down, you will see also health and wellness. And you may think these are the same. Well, this disease and illness actually focus more on the disease and illness, whereas health and wellness works more on the life choices, how to stay healthy, that kind of thing. I have to admit that with the pandemic we just had, disease and illness has become a very popular category. Energy is also one where we try to solve the problem that we have on the planet to make sure that we have enough energy for everyone. And that includes also trying to find more sustainable sources of energy. Next one is environment and climate change, and a lot of people see the link also between environmental and climate change and energy and agriculture. So keep in mind that if the project is very based on climate change, even though it includes a little bit of energy in agriculture or food production, it should be put under climate change, the climate change challenge. If you have a hard time finding in which challenge your project is, or one of your students' project, make sure you contact the Quebec Indigenous Science Fair, and they will help you in finding the proper challenge for the project. And the last one would be natural resources. This is where we ensure that we have enough natural resources to sustain the human population. Keep in mind that if it is specifically related to food, because natural resources have something to do with food, it would go in the food category. Or if energy is also part of natural resources, but if you're specifically talking about energy, it should go under energy. Natural resources is a broader category for those projects that do not fit in energy and in agriculture and food. So those are the challenges. And let's have a little bit of fun by looking at each of them. You will see that at the science fair, they each come with a logo to make it very visible what they're for. So see, here, agriculture would be my project helps ensure food security, sustainability, or competitiveness in agriculture, fisheries, and food production. The second one, which is curiosity and ingenuity, my project helps improve our understanding or address a problem in an area of STEM not covered by the other challenges. So see, that's the catch-all at the end. The only reason it's there is because they are in alphabetical order, but in theory, it should be at the end. Like if your project doesn't fit in any of the other ones, you would put it under curiosity. Digital technology. My project helps improve our quality of life and transform existing products and services through digital devices, methods, or system. Disease and illness. My project helps enhance our diagnosis, treatment, or understanding of disease or the management of physical or mental illness. Energy. My project helps improve our use of current energy sources, enable the transition to alternative energy sources, or reduce our energy footprint. Environment and climate change. My project helps ensure the quality of water, air, soil, or diversity of living things, or manage the impact of climate change. Health and wellness. My project helps prevent disease or promote physical, social, emotional, spiritual, environmental, occupational, or intellectual well-being. See, it's not only physical here. That's extremely important. And natural resources. My project helps ensure the sustainable management, use, reuse, or recycling of Earth's finite or renewable natural resources. So, let's do a little bit of practice here. I have the challenges on the right-hand side, and we have a project here. Let's read it. The purpose of our project was to find an alternative fuel resource in hopes of combating global warming by harnessing energy from bacteria. By adding sugary additives such as brown sugar, corn syrup, or yogurt, we hope to increase the electrical output of bacteria in a microbial fuel cell. Under circumstances of high resistance, bacteria with yogurt produce more power than additives used. So here we have a project, and I'm going to encourage you to pause the workshop, try to find which of these challenges this project would be in. So hopefully you had a chance to think about it, and you may think, because we saw global warming, so we may think it's under environmental and climate change, and that would make sense to put it there. But this one was actually put under energy, just because it focuses so much on energy that we put it under energy. Now this one, we're hearing a lot of these days about smart cities. Smart cities use technology to benefit the community and to solve everyday real world problems. The mobile application that has been developed is called Bumpometer, and it's aimed at both solving a real world problem or detecting potholes, bumps, as well as increasing collaboration and communication between the municipality and the residents through social media. So the students created an app, and the app is to report potholes and bumps on the road so that they can get fixed faster. So I'm going to invite you to pause the workshop, think about it, and then decide in which of these challenges you would put this project. So hopefully you had a chance to think. This one will be under digital technology because it involves app creation and it's managing a database of information that is provided by the citizens. So that would be a digital technology project. Okay, so now we know about the different types of projects and also the different challenges. And you already have seen some sample projects. It gives you an idea of the kind of projects that we see at the Quebec Indigenous Science Fair as well as Canada-wide Science Fair. All these projects that I just showed you were participating at the Canada-wide Science Fair. Now, one of the things that we will be using as part of our workshop today is the Smarter Science framework, or if you work in French, it would be EXPO-SCIENCES. This framework has been created by Youth Science Canada and is designed to support teachers in the implementation of project-based learning as well as inquiry-based learning. And when students are working on a science fair project, they're doing an inquiry. They're investigating a question, and they're trying to answer these questions either using an experiment, a good research, or by innovating and inventing something. Now, a lot of the resources that I'll be presenting over the next few minutes are available on the Smarter Science website. And to go there, you just go on smarterscience.ca, smarterscience.ca. It takes you to this part of the workshop, and you will find a section called Resources, which will take you here. So today I'll be using, you'll see on the wall, I'll be using posters. And these posters, if you click download, it's going to take you to a SharePoint where you can download those posters. So that's very useful to know. A second thing is I'll be using a booklet. So you will find a booklet right here. That easy. And it's in PDF. You can download it. And you can also download it on the French website if you need it in French. So this is where you will find the Smarter Science resources on smarterscience.ca under Resources. Now, what is Smarter Science? Smarter Science is actually a framework to support you as a teacher and to support your students to make sure that they all do good science, science that is valid, but also giving them some freedom in what they do. So, the Smarter Science framework focuses on global competencies, those thinking skills. And these are creativity and innovation. If we always get our students to do science experiment, perform science experiment that are in a textbooks, students are not creative. They're not becoming innovative. They're basically following a recipe. They're doing a step-by-step that is provided in their textbook. When students are doing an experiment project as part of the science fair, they will be coming up with their own experiment. They will be creating, brainstorming variables for their own experiment. They will also be using critical thinking and problem solving. And one thing that is extremely important to realize is critical thinking is not criticizing. Critical thinking is to be able to establish criteria, success criteria. So when they're inventing something or creating something, what are the criteria that determine if their science experiment or their innovation is successful? And sometimes criteria will be different from one project to another. Let's say I'm coming up with an invention. Maybe my invention, for me, the most important thing is ease of use because my invention is for the elders. So I want ease of use as being my number one. Maybe for another student, criteria number one would be sustainability, protecting the environment. So they want their invention to be green. Maybe for another group of students, they are creating an invention that is aimed at people who have very little money. So maybe the cost will be the top criteria. So depending on who the target audience is for the invention, the criteria will be different. So students need to establish those criteria and rank them. What are the most important criteria for my experiment? And imagine when they're presenting to the judge, they should say, these are my top criteria, and I made sure that when I created my invention or my innovation or even my experiment, these were the criteria that I was trying to reach. Obviously, they will be doing problem solving. When you perform an experiment or when you're looking for data for a research project or when you're coming up with your invention and you're building your prototypes, it never works the first time. I can guarantee it. So students have to problem solve. Especially if they're working in a group of two, they will need to collaborate because there's teamwork involved. And even if they're not working in a pair, if they're doing their project solo, they still need to collaborate. Maybe as part of their research project, they will need to conduct an interview. So they will need to collaborate with someone for the interview. Maybe they are performing an experiment on humans. And if that's the case, make sure you contact the Quebec Indigenous Science Fair because there's some important rules regarding using humans for science fair. But let's say they use humans in an appropriate way. They need to collaborate with these humans to perform the experiment. So there's a lot of teamwork, collaboration. What we want with science fair is students to take initiative. We want them to become a little bit more autonomous. And we want students to become young entrepreneurs. An entrepreneur doesn't necessarily mean earning money, getting a lot of cash. No, it means to start a project, to bring their project to the community. So if they create something that could benefit the community, like we want them to go and talk to community leaders and say, hey, this is what I created. It could support our community. Let me implement that in our community. That's what we want. We want projects that will be useful for the community. The projects are not necessarily just theoretical. They're useful for people. You're trying to help someone, or you're trying to help the environment, or you're trying to help an animal. You're trying to help society. Those are very rich science fair projects. Obviously, as the students are working on their science fair project, they will need to be good communicators, either through their project report, or they need to do good graphical design for their display board, and they need to be doing good verbal communication as well. And the more and more, when students are working on science fair project, they will be working on their digital competencies. Even like creating their board could involve doing some, graphic design on a computer. Or maybe as they're collecting data, they may be using the sensors on their phone to collect data. The more and more we see technology being included in science fair projects. So, when you are doing science with your students, not only for science fair, but also for any science course that you're teaching your students, there's 4 levels of inquiry. In many cases, students will be doing confirmation inquiry. In a confirmation inquiry, the students will study the subject in a textbook first, then they will perform the experiment. They will, let's say, learn the second law of motion, Newton's second law of motion. They will know the relationship between force, mass, and acceleration. They will know the formula. They will have done a lot of exercises in their textbook. And they go in the lab to confirm something they already know. So they are not discovering the concept through their science experiment. They're just confirming. So in this case, the teacher is providing them with a question, like what is the relationship between force, mass, and acceleration? The teacher is providing them with the method, how to do it. So the step by step in the lab, they will say like you need a little cart and you will need a little weight and a pulley, and then you will measure the acceleration this way and you will increase the force this way. So you provide all the method, and you also provide the analysis ahead of time, because students already know the answers. They know the formula. So they're just confirming what the teacher taught them. The second level of inquiry is called a structured inquiry, where the teacher will provide a question. As an example, I'd like you to see the relationship between the amount of sugar that I put in my recipe and the carbon dioxide produced by yeast. So I provide them with the questions, and I even provide them with the method. I say you will have 4 containers. In the first container, you will put 0 gram of sugar. In the second container, you will put 100 gram of sugar, then 200 gram and 300 grams. You will use water at 25 degrees Celsius. You will use 1 teaspoon of yeast. You will put a balloon on top of it to collect carbon dioxide being produced. But I'm not giving them the answer. They don't know if more sugar or less sugar is better. So in a structured inquiry, students at least have the fun to find the answer. But the method and the questions are provided to them. Then we move to the next type of inquiry, which would be a guided inquiry. In a guided inquiry, we provide just a question. As an example, let's say we're building electromagnet using wires around a nail, and I'm asking them, what is the relationship between the number of turns that we will do and the strength of your electromagnet? I'm not providing them any method. I'm not saying you're going to use 5 nails, you will do 0 turn on this one, 100 turn, 200. I'm not providing any method. And I'm not giving them the answer. I'm just providing them with a question. They get to come up with the method and the answer. Now, the last level, and this is the one we hope you will implement for science fair, is an open-ended inquiry, in which the students will come up with their own question. Once they have a question, they will come up with their own method to answer this question, and then they will find their own answer. A lot of teachers will not want to do this for their regular teaching, basically covering the Quebec progression of learning. And they're afraid that if students come up with a question, they will not reach those objectives that they're supposed to reach as part of the progression of learning. Now, what I'm going to show you soon is a technique that you can use to cover your curriculum through open-ended inquiry, where what you do is you bring a spark, you bring a starter, you bring something in the classroom that will surprise your student and will get them to ask questions. Now that spark, that thing that you're bringing in the classroom, will obviously be linked to your curriculum. If you're trying to cover a unit in chemistry, you're going to bring something that is chemistry based. If you're doing a chapter on electricity, you will bring something that is electricity based. If you're trying to cover some like yeast, you will bring yeast in the classroom. So you bring something that will be linked to your progression of learning, but you let students ask their own questions. In this case, this spark or this thing that you're bringing, and I'm going to give you a few examples throughout the workshop, is something that is carefully planned. In French, we call it la ruse pédagogique. So it's kind of a way to bring questioning by giving the impression to the students that they come up with all their own questions, but you've designed this spark so well that there's no way they will not come up with any questions. Okay? So it needs a bit of practice as a teacher to do that, but it's a great way to get open-ended while covering the curriculum. Now, for the science fair can be about anything. So any questions that they have, that's awesome. You don't even need to bring a spark. You may have to bring a spark for students who have a hard time coming up with a subject, but in general, it's better if students do something that interests them. If they like cross-country skiing, that should be about it. If they like skidoo, it should be about it. If they like fishing, their project should be about fishing. If they like snowboarding, or if they like skateboarding, or if they like cooking, the project hopefully has to do with their passion, something that they're passionate about, and something that they feel good about, that they can help people. Now, I do have a few questions here. Now, some of these questions can become great science experiments. Some of them are not good questions for a science experiment. Actually, I'm going to give you a hint. 2 of these questions would be great for a science experiment, and 2 of them would not be good for a science experiment. So I want you at this point to pause the workshop, think about it, have a discussion with your colleagues, and then come back and see which one would be a good science experiment. So hopefully you had the discussion with your colleague. So if we look at the first one, does the Japanese tsunami impact the climate where I live? That's the tsunami, I think, was in year 2010, around that. It would be hard to do an experiment for that. Would be hard. Let's say I recreate the tsunami, I may have problem. People may not be happy. It would involve, moving the bottom of the ocean. That will not be possible. Now, there's ways to try to answer this question. I could do research on historical data. Whenever there was a tsunami, use Environment Canada, that would be an option. Or I could do a small-scale model, or I could even use a computer model, but not an experiment. So the first one was not a good experiment. The top right one would be a good experiment. What is the best sunscreen? However, we need to improve this question. Because what is best? Like, are we talking about what is the sunscreen that provides the better hydration, the better protection, the longest protection, the most waterproof protection? Like, we need to define best. And that's part of critical thinking. When we're talking about critical thinking, this is where you want to have criteria. What do we mean by best? But it would be a good science experiment that could be done. Maybe not on human, though. It should be done on non-human. And if students plan to use animals as well, they should also contact the Quebec Indigenous Science Fair to get their project approved before they start any experiment. Now, the bottom one, bottom left. What is the link between juvenile obesity and the consumption of carbs? This one could be an experiment. However, it is using human, and this would not be approved at the science fair. It would not be ethical to take half of the class and have them eat a lot of carbs this week, and half of the class eat no carbs, and see how bigger they get over the weeks. That is not ethical. Now, is there a way to answer this question? Totally. I could do some surveys, large scale, because small scale may not give proper results. But when I'm doing a survey, I'm doing a research project. I'm not doing an experiment. So I'm collecting data, and I'm not bringing variables. I'm just trying to see trends in data and recognize the limit of that. Sometimes there are many factors that may affect the obesity more than just food. So students need to recognize different elements of lifestyles and maybe include these in the questionnaire. Now, always remember that when students do science fair project that involves human, even surveys, there needs to be informed consent from an adult. So doing a survey on your friends at school is fine as long as there is an adult, a parent, that has approved that. So each participant should have a parent sign a form in which they are stating that they understand what the data will be used for. The last one is totally an experiment. How does the temperature influence the mass of sugar that I can dissolve in water? This is purely an experiment. We have a dependent and an independent variable, so that's an experiment. So the ones on the right are an experiment, although the one on the top right needs to be redesigned a little bit. The ones on the left would not be answered with an experiment, they would be answered with something else. Now, as part of the Smarter Science, we also have a poster. And I showed you a bit earlier how you can access those resources by going on smarterscience.ca and looking at resources. So this poster has all the verbs that students should learn as they complete their education in science. So, as they're doing a science experiment or an innovation or research, students will need to initiate and plan. You don't go in the lab immediately, you have to initiate and plan. You will notice that I said the word lab. And at Smarter Science and at the Science Fair, we have a very broad definition of a lab. A lab is not necessarily just the lab that you have in a school with beakers and Bunsen burners. No, a lab can be in many things. And I do realize that in some communities, a lab may not be available, like a traditional lab. But a lab could be a river, a lake, a kitchen could be a lab, a garden, a garage, a shed. All of these things could be a lab. The beach could be a lab. The forest could be a lab. A ski hill could be a lab. What we traditionally call the field versus the lab can all be called a lab. So before students go in the lab, so creating their experiment, they need to initiate it. They need to make some decision. They need to plan the experiment. Then they would perform and record their data, perform the experiment and record the data. Then they will analyze and interpret. And finally, the last step, they will communicate, including presenting their science fair project at the fair. As you see on the poster, we have an increasing level of difficulties. Skills at the top of the posters are a lot easier than the skills at the bottom of the poster. So observing, questioning, searching, interviewing, comparing, contrasting, discussing, explaining are a lot easier than skills like modeling and selecting and inventing and analyzing and defending and teaching. It's a lot harder to teach than to discuss. So as your students are learning, if you're teaching middle school, you may want to focus on the skills in the middle. If you're teaching in kindergarten, grade 1, grade 2, grade 3, you may want to focus on the skills at the top of the poster. Like when I'm working with kindergarten, grade 1, I do a lot of observing and questionings. We compare stuff, we contrast stuff, we discuss, and we start doing basic measurement. As students get older, I'm going to focus on the skills at the bottom of the poster, which are higher thinking skills. And if you've used a Bloom's taxonomy at the teacher's ed, we've tried to include all the levels of the Bloom's taxonomy as part of our poster. Now you will also see that we've included the 5 E's lesson plan. So as you initiate and plan, you need to engage the students. And this is where I said you need to bring a spark, something that will impress them, interest them, start the questioning. Then as they are performing the experiment, they will be exploring. As they are analyzing their data, they will be explaining the data they got. And then as they're communicating, they'll be extending their knowledge. Now, this is 4 of the E's. The 5th one is actually at the bottom, and you will see that it covers the whole thing. And this is extremely important. A lot of people think that evaluate should happen at the end. And at the science fair, this is a bit what happened. We evaluate the final presentation. We evaluate the display board that is behind them. We evaluate their project report. But as a teacher, you need to do more. You need to evaluate every steps of the way. You need to be there when students are planning the experiment and assess that. You need to assess when they are performing the experiment. So you need to be observing them as they are performing and recording their experiment. As they're analyzing their data, you should be there and assessing and evaluating what they are doing. So the assessment is happening during the whole process. Now, this brings me to judging. Unfortunately, judges don't have access to the students when they were initiating and planning, when they were performing and recording, and when they were analyzing and interpreting. They only have access to the students when they're communicating. But we have technology these days. We can take photos, we can take videos. So please try to document the other 3 steps as much as you can and put this on the display board or on an iPad or a device, a phone in front of their board, or maybe print some of these photos just so that the judges can see the whole process and not just the end. One great thing about those skills that I just showed you that are on the Smarter Science posters is they are transferable. Even though you're teaching science, you may be teaching other subjects, especially if you are an elementary school teacher. These skills are also useful for history, geography, French, English, phys ed, arts. All of these skills, you would be using them. Like I have students in history and geography observing and questioning and interviewing and comparing and contrasting different periods of time. So they are very transferable. You will also notice that our Smarter Science poster contribute to literacy and numeracy. You will see that the first column and the last column are very literacy based when it comes to like inferring and observing and communicating and discussing. And the 2 middle ones are very numeracy based when it comes to collecting data and creating a graph and a chart and analyzing the data. This is all very numeracy based. Now, there's another tool that will be useful to you, and it's a booklet. This booklet is called Introducing the Framework. This booklet is actually complete with definition, and each of the process skills is fully detailed. So the process skills are the skills we just saw. And this booklet has it all. The idea is to provide you with what your students should be doing and not doing when they are using those skills. So let me give you an example. This is a page from the booklet. And if you ask me, where do I get this booklet? Remember, you go on the smarterscience.ca website, you go under resources, and you can download the free booklet. So for observing, first it will describe what observing is. This is a definition that you will also find on the poster, but because in the booklet there's a little bit more space, we have a bit more details in the booklet. Then, this is the important part. It's going to tell you what students should be doing and not doing while they are observing. So students should be using all 5 senses as appropriate. They should be detecting details in natural phenomena that go beyond that of a casual observer. They should be building understanding by connecting to past experiences. But they should not be limited to sight and touch. They should not be using simple words like, oh, it's cute, it's fun, it's nice, it's cool. They need to use descriptive words. They should not be attributing cause to the observation. Now, if we go to the bottom of the page, you will see that this is what the teachers should be doing when students are observing. So as an example, the teacher should be prompting students to use all 5 senses. That's okay. The teacher should be encouraging students to use expansive, descriptive vocabulary, including all the scientific terminology. The teacher should be encouraging students to make connections to past experiences. But you also have what the teacher should not be doing. The teacher should not be telling students to notice specific aspects. Teachers should not say like, oh, did you think of looking under or inside? No, let the students do it. And the teacher should not be expecting every student to notice the exact same details. That's okay to not notice the same details. Now, what these skills should lead to. In this section, you have the connection between the different skills, because that's those skills, that the 35 skills you saw in the posters, they are connected to each other. As an example, to compare and contrast, you need to observe. To infer, you need to observe. So observation is linked to those skills. Another example, to be able to graph data, you need to collect data. So there's a connection between these two skills. Let me show you another skill. So this is inferring. So see, for inferring, we have the definition. We have what inferring is for the students, what it is not, what inferring is for the teacher, and what it is not. So let's practice some of these skills, and this is just a few ideas of activities you can use with your students to practice those skills. So in this one, it's super simple. You grab some newspaper, those comic strip, and these are available online now, and you just hide the end of the story. And you get students to predict what will happen next. So, as an example here, I hid the rest of the story, and all the students see is the first frame. First frame says, "Do you need a ride home, Dr. Duncan?" And he says, "No, Jeremy is picking me up at 5 p.m. Sorry, at 5. I don't want to add p.m. It doesn't say p.m. here. So I get students to predict what happens. Now, if you look at the definition of predicting, it says that a prediction should be based on observation, prior knowledge. So what kind of prior knowledge and observation can you make here? A prediction it's not a guess. You need to back it up. So whenever students are creating a prediction here, I'm asking them to back up their prediction. Oh, I think this and this will happen. Why do you think this? Now, this activity may not look like it's science in nature, but keep in mind that when students will be working on a prediction on a science fair project, or for a science experiment, and they don't remember how to make a prediction, I will remind them. You remember when we did this activity with the comic strip? I want you to do the same thing. You're going to predict what's going to happen with the chemical reaction here. I want you to back it up with prior knowledge and with observations. So if you want to take a pause, discuss with your colleague what's going to happen here, then I'm going to take your prediction in a minute. So, I don't know what your prediction was, but this is the end of the story. He should be here any minute. Any minute. And a lot of students, when they predict, the first thing they'll say is the end needs to be funny. And why do you think that? So I asked them, why do you think that? Well, because all of those comic strips are funny. Okay, you have prior knowledge. See, I insist on what they say. So when they predict for a science experiment, what is your prior knowledge that you have about this? Oh, okay. It's let's say it's a polymer. Okay, what do you know about polymer? How will this help you predict what's going to happen here? See, you get them to come up with their prior knowledge. Now, this second activity is different. It looks the same as the first one, but in this case, we are inferring. We're not predicting. We're not trying to see the future here. We have the future, or we have the present, I should say. What we want to do is to infer what brought us to this scene. I use these two activities one after another to differentiate the difference, to differentiate inferring versus predicting. In this case, I don't care about the future. I don't care about what's going to happen next. I want you to infer what brought us to this situation. You can always make connection with police investigation. Police investigation, when there's a crime scene, they come to the crime scene and then they have to infer what happened. Now, they don't infer by guessing. Again, they infer based on prior knowledge. They do have training. They are investigator, scientists, police officers, so they have some training. So they have prior knowledge. And they are also making observation about the actual crime scene. So, I want you to pause the video, have a discussion with your colleague, your peers. What brought us to this? So, you may have a variety of answers here. What brought us to this? I had so many from students. Like some student says, oh, he's a robber. He stole that snowboard and he was inside the store and then he dug a hole to go underground so he wouldn't go out through the door and get caught by the security system. I have students who say, wow, this is, he doesn't have enough money to go to a ski hill, so he is skiing in a parking lot. So many different answers. Again, when they give me an answer, I want them to justify with prior knowledge or observation. And there's so many observations students can make here. I don't know if you can notice, but there's some shopping carts at the bottom. A lot of students notice that all the cars are the same. Some students notice that there's those same kind of little hills. You see them on the side. Some students say it's a Walmart or Value Mart or something Mart because we see Mart, so they assume it's a store. Some students assume that it's a teenager. And when I ask them to infer why, well, they say only a teenager would wear a cap and a hat and a hoodie like this. So I have many different answers. Now, this is the official story. Mom, I really, really want to go snowboarding over Christmas break. It doesn't matter where you want to take me. It could be Mont Tremblant. It could be Whistler. It could be anywhere. All I need is a snowy place to hang out. And the mom gives him a kiss and say no problem. And she takes him to the to the parking lot where there's the pile of dirty snow. So again, doesn't matter what the story is. The idea here is that your students get to infer and see the difference between inferring and observing. This is another one that I like to use in the classroom with the students, where I get the students to actually infer what they are looking at. And for this, let me take you here. I have a video called Zia. Actually, let's go and get it online. You will find it online. Zia, it's from the National Film Board. It's a video online. Here it is. ZEA by the National Film Board. And you can play this video for your students. And basically, as the video is moving, students have no idea what they're looking at. Like, I have them, and I won't do it the whole thing with you right now, but they make like a bunch of observations. A lot of students think at first that they're looking at a planet, and because it's round and it's dark in the background, and then they see something like this and they go, what could that be? Oh, they say there's a source of light. That's one thing that they say because it's reflecting. And then as they reach this part where they see a drop of liquid, they say, oh, so it can't be a planet. This is small. This is not huge. And as the story goes, they have like, at this point, they think it's an egg yolk. So they have all sorts of inferences. And with every inferences, I ask them to justify it with either prior knowledge or observation. I don't accept just an inference. And then as they keep going, they're going to see the bubbles. At this point, they say it's a fish. Sometimes they hear it's a fish. See the front here. Some will say, it must be hot and it's bubbling, so it's like boiling. I hear that a lot. So I get all of their explanations. Some say it is the egg being fertilized inside the mummy. I hear like so many stories. And at this point here of the video, this is usually when they have the actual real inference, the reality of what it is. And it's basically a kernel of popcorn popping. So I really like to use this video with students. So Zaya, just to work, you make observation, you infer, you base your inferences on observation and prior knowledge. So all of these are designed, these activities, to practice those 35 skills before you even talk about a science fair project. You want students to acquire those skills, and then you can start working on the science fair project. So I do have an activity here that we're going to do together. It's super easy. It's called the pengocopter. So I'm going to move to the studio where we're going to perform this and use the posters. Now, the pengocopter is a very simple experiment. I do it because it's so simple. All you need is paper clip, scissors, Post-it notes, and it helps students understand the idea of having a proper experimental design, to properly design an experiment and follow all of the rules of science. Now you will see that the cool thing is this is a spark. I bring the spark in the classroom and students brainstorm. Now, would this penguin become a science experiment, a science fair project? Probably not. It's to build the understanding of the experimental design. But when they are working on their actual science fair project and they have a hard time identifying variables, I would go back to the penguin and say, you remember when we did the pengocopter? Remember we did those variables and this and this? Oh, yeah. So the idea is to build with something so simple as the pengocopter, just so that they understand the scientific method, and when they need to use it in context for the science fair, they already know about the experimental design. We're going to have a second one as well. The second one will be using instance no. So you will see that we will also brainstorm variables using instance no. Now for the pengocopter, I will build a pengocopter in front of them, but then I'll ask them to create one that behaves differently. And we will be using the steps to inquiry poster. That's going to be our second experiment. So the mystery powder, I already told you it's the instance no, but for the students, we call it the mystery powder. Okay, so let's go in the lab, in the studio, and we're going to explore these science experiments. So welcome again. Let's see how we can use the pengocopter to get students to properly understand the scientific method, which means that they can identify variables, determine the independent, the dependent, and the control variables. We're going to be using those posters. And again, thesthese posters are available on smarterscience.ca for free under the resources section. And you will see how we can use these in the classroom to build this understanding of variables. So, my spark. This is how I would go about it. And even though you're not teaching flight as part of your curriculum this year, it's possible, I would still encourage to do this science experiment just as a way to get students to understand the scientific method. So, I have some material on my table here. I would have a bunch of penguins. And I just take a clip art of a penguin. I try to convey messages as part of my spark to ensure that students will have diversity in the penguin that they built. So I would have different size penguin. Same thing with paperclip. I would make sure that I have paperclip of all sizes and shapes and colors, like a variety of them. And then Post-it notes. And again, I would have a bag of mixed Post-it notes available. And I may even include scissors on the table, just in case they decide to use scissors and cut something. That's totally fine. As part of a Smarter Science Spark and experiment, there's always some playtime. There's a 10-minute. I wouldn't give more than 10 minutes, because if you give more than 10 minutes, there's a chance that they may do a full science experiment. I want to give them just a little bit of time to come up with some ideas. So basically, I would ask them, make sure that you create a penguin that behaves differently, that doesn't behave exactly the same way. So I would build one in front of them. So I'm going to be using just a penguin with a paper clip on the bottom here. And I will put 2 wings on it. I'm going to use the Post-it note as wings, like this. And like this. And then I would demo it. And students, I don't know if you could see, but in my case, the penguin is rotating. Mine is rotating counterclockwise at a certain speed. So obviously all of these could become things that we want to observe in the future. So at this point, they've seen my penguin. I want to give them some time. Playtime, anything you want to do, as long as it's safe and we're not wasting materials. I have students say, can I use more than 1 paperclip? Yeah, go for it. Can I put it in a different place? Yeah, go for it. Can I put more than 2 wings? Yeah, as long as you're trying something that you want to test and you're not just wasting Post-it note. Yeah, go ahead. Can I cut the Post-it note? Yeah. So there's a lot of freedom at this point. So if you want, I encourage you to take some time, pause the workshop, photocopy a penguin, just find a clip art, get some paper clips and some Post-it notes, and create your own penguin. And then come back. Okay, so I assume you've come back and you're ready for the second part. So now we have a bunch of penguins coming from all the students in the classroom, and we have so much variety. They're all different. They're all looking like, some have like shapes, different shapes of wings. Some have the paper clips everywhere. Some are using double penguins, smaller penguin. I've seen penguins horizontal. I've seen penguins with like wings all around. I've seen many things. At this point, it's important to bring all of those penguins at the front of the classroom, because the goal of the playtime or the exploration time was to come up with a bunch of variables. And hopefully your students have a lot of diversity. If all the penguins look the same, it's going to be hard to move to the next step. Then I'll be using some purple Post-it notes and some green Post-it notes. And the reason I'm using these 2 colors is these are the colors used on the posters. So the posters are designed to make it easy and foolproof to do science with them. And as you will see, they are part of the initiate and plan. So we're still in the first column of those 4 steps to a science fair project. Initiate and plan, perform and record, analyze and interpret, and communicate. We're still planning the experiment. And so far, the playtime is not an experiment. It's a brainstorm. We're going to perform the experiment after that. So let's grab a Sharpie here. And this is where I would have all the students come to the front of the classroom and look at what everyone else has done with their penguin. And we will brainstorm ideas. So the first question here is, what did I observe? So I asked students to observe mine and observe all of their friends. So some will say, oh, it turns. Oh, it does a certain number of turns. Okay, so that's an observation. We have different number of turns. Some will say, oh, sometimes it turns clockwise, and on other penguins it turns counterclockwise. So the direction of the turns is not always the same. Direction of the turns. Okay, let's add this as an observation. Some will say, Oh, my penguin take a lot more time to get to the ground. Okay, so the flight duration or the flight time is different. Okay, let's add this to our observation. Don't forget, it's only one observation per post-it because the post-its will travel from poster to poster. Some will say, my penguin smells like paper. You take anything they give you. It's not time to judge right now. Some will say, oh, some penguins go faster, some of them go slower. Also, the speed is different. Okay. Some will say, oh, some penguins are flying horizontally, some penguins are flying vertically. Oh, okay. So the orientation during flight. They have different orientation during flight. Okay, let's take note of that. So those are observations. Some will say, oh, some penguins have a bigger mass, some have a smaller mass. So the mass of the penguin is different. Okay, so you note all of their observations. Some will say, when it falls, sometimes it makes more noise, sometimes it makes less noise. So the sound level on impact may be different. Okay, I noted. So now I have from my students many observations. Now that's when you have enough, you filled it, you're going to switch to the purple. And the purple is the question. So I have students asking, can penguin actually fly? I write their question. Can penguin fly? Okay. Some students will say, well, what happens if I put more or less wing? So the number of wings, does it affect my penguin, the number of wings? Some students may say, oh, I noticed that on some penguin, the post-it are higher, sometimes they're lower. Oh, so the position of the wings is different. Does it affect my flight? Okay. Some will say, oh, I noticed that maybe they are in the same position, but they have different angles. Oh, the angle of the wings. See, we're starting to get the science vocabulary here. Angle of the wings. Some will say, oh, some penguins are smaller, other and are larger, so the size of the penguin. That's why you want all of them to be on the table at the front, so you can see all of them. Some of your students may say, oh, some have different shapes of wing, because some students cut the wings and they look like a triangle instead of a rectangle. Okay. So the shape of the wings. Does it affect my penguin? Okay. Some will say, oh, some have bigger wing, some have smaller wings. Oh, so the area of the wings. The area of the wings. Okay, that's interesting. Okay, so let's have a look at if we have other questions. Some students say, oh, I've seen some of us made it with paper, other made it with cardstock. So the material used for the penguin. The material used for the penguin. Okay. As you can see, we're brainstorming variables right now. Some say, oh, when I drop it, I push it, but some of my friends just, open their fingers and let it fall. The way you throw it. Does it affect the way you throw it? That's a nice question. Some will say, oh, I've seen some friend drop it horizontally and some vertically. Oh, so the initial orientation. Earlier we were talking about the orientation during flight, but now we're talking about the initial orientation. Maybe this will affect. So, some may say things like the color of the wings, and maybe you will disagree that the colors of the wings would have an effect. But you will still write it, the color of the wings. Okay. So now once you have all of your observation and you have all of your wondering, your questions, now comes the next step. So the post-it will move from poster 1 to 2 to 3 to 4. At each step, some of the post-it notes will not make it to the next steps, and that's totally fine. And students should not feel bad for having a post-it that doesn't move to the next poster. So let me show you how we move from this to this. We have observation. Some of these observations will become possible dependent variables. Possible dependent variables are variables that I can measure, but I cannot choose ahead of time. As an example, I could measure the number of turns, I could count them, that my penguin will do. But I don't get to select this ahead of time. I don't get to say, penguin, this time you're gonna spin 7 times. I don't get to choose that. So it's gonna move here. The duration of the flight. I don't get to select if my penguin will fall for 10 or 12 or 5 seconds. I could do things that will change that, but I don't get to select this value ahead of time. So it would be a good possible dependent variable. Then, the direction of the turn. I don't get to select if it's going to turn clockwise or counterclockwise. I could do things that would affect this, but I don't get to select this ahead of time. So it's going to become a possible dependent variable. The speed, I don't get to choose if it's going to fall quickly or slowly, so the speed would be a good possible dependent variable. And all of these are pretty easy to measure or observe during the flight. The smell. Smell is kind of hard to measure. So this one's going to stay here. That's an example that will stay here. Now the orientation during the flight, I could measure the angle at which it's falling. And sometimes I mention digital technology or digital competencies. That's an example where you may need to take a video with your phone and then measure the angle. Now, the mass of the penguin may sound like something that we could measure. However, we can choose that. I can make a penguin that's going to be 5 grams or 2 grams. So this one's going to stay here because that's something you can choose ahead of time. Now the sound level on impact, I don't get to choose how many decibel it will make when it hits the ground, but that's something I could measure, so it's going to come here. So see, most of the post-it graduated to the second poster, but not all of them. And that's okay, that's fine. Now from the second set, I need to see what are some of the things that could affect these 6 variables that I choose here. What could affect the number of turns or the duration of the flight or the direction of the turns or the speed of the penguin or the orientation during flight or the sound level on impact? Well, maybe they'll say, oh, the area, the surface area of the wings would affect these things. Okay, that's a good one. Maybe the angles of the wings will affect these things. Maybe the position of the wings will affect this. Maybe the number of wings will affect all of these. Maybe the size of the penguin would affect. Maybe the way I throw it will affect. Maybe the material used for the penguin will affect. Maybe the shape of the wing will affect these things. And maybe the initial orientation will affect these things. So I'm going to take these ones and put them here. Now, I'm left with can the penguin fly and the colors of the wings. Can the penguin fly? It's more of a research question. I want to do some research on penguins. Can they fly? I want to check maybe in a book, in an encyclopedia, on a website. So that's a research question. It's not a good variable. So it's a good and valid question. It's not just a good variable. So that's why it stays in the first poster. The colors of the wing, you may have students who will argue that it could affect my flight. If they totally argue, you could bring it here. And the worst that will happen is they will do an experiment and realize that it has no effect. That's okay. Okay, so now we have poster number 2 done. That's good news. We're ready for poster number 3. Poster number 3 has a very important purpose. I've seen so many science fair projects where students have too many variables. They just work with too many variables at the same time. So the experiment is not valid because they're just having too many variables and you don't know which one has an effect on which. This forces the students to choose only one independent and only one independent and only one dependent. So only one from the green and only one from the purple. Which means, let's say they want to do the flight duration. And let's say they are interested in the angles of the wings. Like this. Angle of the wings. And the flight duration. So, now, all the other variables become control variables. See? And I say there's 6 boxes, but if you can fill more, that's going to make me very happy as a teacher. Make your judges very happy at the science fair. The more control variables you have, the better. So see, it forces them to isolate one as the independent and have the other ones as controlled variables. So now we have a questions. If I change the angle of the wings, what will happen to the flight duration? And now see, look how easy it is. From poster 3 to poster 4, you copy and paste. And now we have a scientific question. If I change the angles of the wings, what will happen to the duration of the flight? Considering that I keep all of this controlled in all my tests. And this is where the students will write their hypothesis. If the angle of the wing is increased, then the flight duration will be reduced or increased. At this point, it doesn't matter if the hypothesis is false, because they're going to perform an experiment to check if it's true or false. However, it could be poorly written. If the students say, if the angle of the wings is changed, then the flight duration will change, this is not even a properly written hypothesis. It's not that it's false or true, it's just that you can't verify that. It doesn't show the direction of the change. So here the students should use the word increase and decrease. And I encourage you to download these posters to actually see exactly the wording that is used on the poster. I realize that on the camera here, it may be difficult to read every single things on it, but if you download them, you'll have a better read of them. Now, one of the cool things is you could have a team work on the angle of the wings, and you could have things working maybe on the position of the wings. Then you can have a team working on the area of the wings. So you can easily, you have a machine to create questions, scientific questions. The good thing is a lot of students have a hard time writing a proper scientific question. I'll see a lot of questions like, what is the best penguin? You remember earlier we said, like, what is the best sunscreen? That's not specific enough. You need to have those variables in the question. So when your students are working on creating a questions for an experimental design science fair project, they need to include those variables in the questions to make it clear what they're looking for. So let's have a look at a second example of a spark that you can bring in the classroom to teach the scientific method so that when your students are ready for the science fair project, they know how to target their variables. So we're going to be using the poster again. For this one, I use sodium polyacrylate, also known as instant snow. So if you have access to Amazon or any reseller, Toys R Us, usually those stores will have instant snow, also known as sodium polyacrylate. It is a super absorber. It's a polymer, so it will absorb its weight and then grow to look like artificial snow. I also like to order it from movie sets or movie equipment stores. Thomas Effects in Vancouver is one that I really like to order. So depending on where you have access to order, may affect where you will order it. If you want to use this one, I find this one is really great at getting students interested in science, and also the variables are a little bit more difficult than the penguin, but they're still quite simple, and it's also a substance that is not very dangerous. So it's super easy to give them that freedom in the playtime. Again, this may not be linked specifically to your progression of learning when it comes to the actual scientific content, but the goal here is not necessarily the scientific content, but it's working on that scientific method that we have with the poster. So let me show you how it works. So I've got it in a Ziploc bag here. Gonna get a little scoop. You don't need a lot. So when you order it, see I have a huge jar here. That's a pretty big jar. You don't need that much. You just need a tiny little amount. Like I'll put like a very tiny amount here at the bottom of my beaker. You don't even need to use a beaker. You can use any kind of cup. And then I have water. So it's going to work the same. I'm going to ask students to do something that behaves differently. So I use the powder, I'm going to add the water, and as you can see, it grows. See? It becomes a lot bigger than it was originally. I had a tiny bit at the bottom, and it is like already like taking even more than the beaker, almost the size of the beaker, and I keep adding water. It will continue to grow and use more and more space. So now we have like a whole beaker full when we had like a tiny layer at the bottom. So that's my demo. I ask students to do something that will behave differently. So by behaving differently, it can behave a little bit differently or a lot different. So some students will decide to use hot, cold water. I've seen students use juice, Coke, sparkling water. Some students will decide to add salt, sugar to the mixture. Some will put food coloring. Some will say, oh, what happened if I stir the solution, not stir the solution, stir the solution, I mean. Some will decide to do things like add the water in the powder or the powder in the water to see if the order of the mixture makes any difference. Some will try vinegar to see if the pH makes any difference. So I see a variety of things that students want to try to see what they get. Again, at this point, it's just playtime. None of them are doing a fully controlled experiment where they're making measurement. At this point, if they don't measure, that's okay. Because the only goal is to have, at the end, you will know that it's successful if all the mixtures they bring at the front look different. You'll have like different textures. Some will look like wet snow. Some will look like very flaky snow. Some will have more or less at the end. Some will be different color. Like some will be cold, some will be warm. So you want this variety with your student. So now let's have a look at what we would get with the Post-it notes. So one of the things that I often get is the volume of snow, the final volume of snow. because it's pretty obvious that the volume of snow, like sometimes you have a lot of snow, sometimes you have just a little bit of snow, so that would be something that they observe. Some will say, oh, the texture is different, like the final texture. Sometimes we have wet snow, sometimes we have drier snow, so the final texture. Some students may say things like, oh, the final temperature. Some students think it's colder than the original temperature. So the final temperature. I kind of trick them and usually give them cold water to start with. And they don't realize how cold it is. So I want to bring this so that they can start thinking, like, was there a temperature change? Some will say the color. The final color will be different. Some will say it's more transparent, more opaque. So the final color could be different. Some will also say like, oh, the mass of the powder. I put more powder, less powder. So you write everything they tell you, the mass of powder. Sometimes it's okay to bring vocabulary. Even though you write what they say, if they didn't say the volume of snow, but they say, oh, the amount of snow, you may want to bring the word volume, and that's fine. Or some will say, oh, it's hot or cold at the end. Oh, the final temperature. So you bring the vocabulary so that they use proper vocabulary for the variables. Some will say the odor. Like they say, oh, it stinks at the end, and it didn't stink at the beginning. The cool thing about this experiment is I told you it's fairly safe. The only thing I would recommend is during the playtime that you ask them to not put it in their mouth, their nose, their eyes, their ears, any holes in their body, just because it absorbs so much liquid. So imagine if it grows in their belly, absorbs too much liquid, so that's not good. It would be irritating their eyes because it would, absorb all of the water. Once it's mixed with water, then it's totally safe. Like there's no danger at all. So I only ask them, the only thing is they can't taste it. They can smell it, but they can't sniff it. They can listen to it. Some will actually have observation, like it kind of make a little bit of noise, and it does when it is just as a powder. So some will say that the, not the crystal, but the particles are a different size. So we'll put it as an observation. Once you have enough, again, you move to the purple. And let's see what they could come up with. Some will say, is it the same stuff as diaper? Is it the same stuff as diaper? So I would write this question. It's a legit question. Is it the same stuff as diaper? Some will say, can I eat it? And some will have questions that are more variable based. That's what you're looking for. But you still write those questions if necessary, like if they tell you. But some of the variables that may come up would be the initial water temperature. The temperature of the water, will this affect? Some will say, oh, the volume of water that you put could affect. So you write everything that they say. The volume of water, maybe it's going to affect. Some will say the order of the mixture, water versus in water or vice versa. So the order of the mixture. Maybe the order affects the result, the outcome. Some will say stirring or not stirring. Will it affect? And again, even if it doesn't affect, that's something that you will want to control. Okay? Some will say the mass of powder. So the mass of powder, maybe it's going to affect my final result. Some will say, oh, the salinity of the water. Maybe if I add salt to the water, the salinity. Some will say the type of liquid. What if I use oil? If they are older, so type of liquid, they're older, they may mention the pH of the liquid. Some may mention also the time, like how long do you wait? So you write all of their ideas, the time it takes. And now we have a bunch of variables. So we're ready to go to the next step. You can always add more if necessary after the fact. But again, here we would be looking for things that we can measure, but we cannot decide ahead of time. Like I cannot decide what the volume of snow would be at the end. I can measure that, but I don't get to decide originally. I don't get to decide the final temperature. I can choose the initial, but I don't get to decide the final temperature of the mixture. I do get to decide the mass of powder. So this one would stay on the first. The final texture, that might be difficult to measure, but it's easy to observe. I'm going to put it as a possible dependent variable. The final color, I may have a scale from opaque white all the way to transparent. Sometimes the students will need to create their own scale, and that's fine. The final odor, that might be very difficult to measure, so I'm going to leave it here. And the size of the particles, I don't get to choose that. That's hard to measure. I'm going to leave it here. So now we have 4 possible dependent variables. Now we're going to look at our other variables. What could affect the volume of snow, the final temperature, the final texture, and the final color? You're going to see here kind of a trend. It's final. What happens at the end of the experiment. So maybe the mass of powder could affect that. Maybe the order of the mixture. Maybe the salinity of the water. Maybe the pH of my water. Maybe the time I let it sit. Maybe the type of liquid. Maybe stirring or not. Maybe the volume of water would affect that. Maybe the initial water temperature. The other 2 questions are good questions. Like, can I eat it? And is it the same stuff that we put in diapers? They're good questions. They're more research questions, so they will stay there. They're not variables. Again, students should not feel bad for asking those questions. They're not just good variables. So we will keep them for research. And then remember, we need to isolate 2 variables. That's a choice. Maybe I want to work on the volume of snow as my final. And maybe I want to work on the salinity of water. If I choose this, the salinity of water and the volume of snow, all my other variables become fully controlled. Meaning I won't be changing them. The only thing I'm going to be allowed to change from one test to another is how much salt I put in the water. And I will see the volume that I get. Now I could have a different experiment. I could decide to work on the water temperature and see how it affects my volume of snow. But if I do this, the initial water temperature, then the salinity becomes control. So only one should go there at a time. Now we copy paste and we have a proper scientific question. If I change the salinity of water, what will happen to the volume of snow? And then for my hypothesis, these 2 terms here. And if you look on the poster on the website, you will see the wording. If the salinity of water is increased, then the volume of snow will either increase or decrease. They have to justify based on their current knowledge. It may not be fully true, but based on their current knowledge, this is the hypothesis that they want to check. Again, I don't want something like if the salinity is changed, then the volume of snow will change, because we're not saying the direction of the change when we do this. So that's it. That's how we use the poster. At one point, you may want to add variables. I've seen students notice that if we change the size of the container, it affects how the snow can grow, because sometimes it will inhibit growth because the water can't reach all parts of the container. So maybe they want to control the container. So it's okay. It's highly encouraged to keep adding control variables as you start working on your experiment. At this point, we've done the initiate and plan, and now we're going to have a look at the fishbone, which is used to go even further than that in our initiate and plan. Okay, so let's move to the next step. We did the playtime in the lab, in the classroom. Students built either their penguin or they used the sodium polyacrylate, the instance node, as a spark. They came up with variables and they now have a proper scientific question and they have a hypothesis. Before they move to the next step, before going in the lab to actually perform the experiment, because remember, the playtime is not where you actually do a fully developed science experiment, students should use some organizer to better define their ideas and better define what they will be doing in the lab. And in traditional teaching, this was called the procedures. This is what was provided to the students as a step-by-step. Step 1, you will do this. Step 2, you will do that. And students would follow the list of steps. As part of our program, we try to attach all of these steps to variables instead of numbering them. And this is where the fishbone came as a great tool to do that. And I encourage your students to build a fishbone and even display it on their backboard as a way to show their judges that they took into consideration all of these variables. So let's have a look at how we use this organizer. You will find this organizer on the smarterscience.ca website under the posters. This is currently as the level 3 posters. You will find the last slide will be the fishbone. So in the fishbone, see, we continue to use the green and the purple that were used in the previous posters. And I'm just going to annotate them. So students could use markers, they could use post-it notes if they want. I'm going to be using my computer here, a virtual version. And you will see that I get to put text. So I have my dependent variable. So let's go back to the penguin experiment. So my dependent variable was the duration of the flight. Might be different for your students, but this is what I had chosen as my dependent variable. Now, my independent variable was the surface area of the wings, size of those post-it notes. And then I had some control variables. So one of the control variable was the height, the initial height. Write this properly. That would be one. Another control variable that I had was the shape of the wings. I also had the position of the wings. I also had the angle of the wings. Now, as you can see, I only have 4 spots here. I always tell students, if you can repeat this, the tail of the fish, the better. The more control variables you will take into account, the better. So right now on this posters, you have 4 spots, but encourage your students to make that tail longer with more variables. Now for each of the variables, students will be finding the IUT. So how you will what kind of instrument you will be using, the unit you'll be using, and the technique. So as an example, if I take my dependent variable here, my instrument will probably be a stopwatch. Or students could say, I'm going to film my penguin and then play it slowly and see the time code on the video. Older students might be doing this. My unit will be seconds. And my technique, I could say something like, as soon as my friend drops penguin, I will start the watch. When I hear the noise, the impact on the floor, I will stop. So the technique may vary. Again, if students decided to use video, That would be an option. So their technique would be a little bit different in this case. They would still be measuring seconds, but they might even be able to go to milliseconds in this case, because you can slow it down and have a very precise time for the duration of the flight. Now, let's have a look at some of these control variables. Again, for each of the variables, we're going to put the IUT. So for the angles of the wing, I will say that I'm going to be using a protractor. My unit will be degrees. So see, it's forcing students to think quantity. So it's not qualitative, it's quantitative. And then here, all the wings will be 90 degrees from the vertical. So I'm stating what will be that angle that I've selected. And I'm actually taking this into account. Now, the position of the wing, I'm going to be using my ruler. The unit will be centimeters. And then my technique for the position of the wings, all the wings will be positioned, let's say 5 centimeters from the bottom. So see, I have to state how I'm going to do it. You may want to use smaller fonts so you have a little bit more space. Now, in some cases, there may not be an instrument in the unit. Like here, for the shape of the wings, I can just say all the wings will be square. Now, some may argue that I will need something to measure that. I might be using a ruler to make sure that all the wings are square. Initial height, I'm going to be using a measuring tape. I'm going to be using a meter as my unit. And then my technique, I will put a piece of tape on the wall 2 meters from the bottom. So now, as you can see, each of these variables, each of these steps have a variable attached to it. So it makes sense. There's a step and there's a variable attached to it. And students know about the instrument. This is how you can vet an experiment. This is how you can have your right to say no, this is not acceptable. Let's say it's an experiment using electricity and one of their variable is the voltage and they want to use high voltage or high intensity of the current. You can say, no, I do not approve this experiment. You need to change this or that. But when they fill this out, you're convinced that they are ready to go in the lab and perform their experiment. So here we're doing it with a simple experiment like the penguin, but the goal is that once they start thinking about their science fair project, that they will be using this to define their variables for the science fair project. So the last one would be the surface area of the wings. This one, I did it last because it's a little bit more complicated. I'll probably be using the ruler to measure my my wings. I will probably be using centimeter square to as my unit. Now for my technique here, I do need to provide an increment. So I could say the wings will be 0, no wings. So that would be your control. And then 10 centimeter squares, 20 centimeter squares, 30 centimeter squares. And then the students may have to further define here. Because how will that students get 10 centimeter squares? Well, they may need to find what will give you the square root of 10 so that they know the length and the width of their wings, considering that the wings, according to this, are square. So you see, it makes students think. And you want to have some data points here. So 1, 2, 3, 4, 5. You may want to go with 6 data point, keeping in mind that you also have your control variable here, or your you may have your comparison between the 0 and having some wings. So that's how you would use this. Now let's fill out a second one, and this time I'm going to fill out one, I encourage you to do it by yourself before you do it with me, but it would be to use it to do the instant snow experiment that we just did, just as a practice, so you can stop the video, fill it out, and then check with me after you've done it. So let me do it here. So the volumes of snow was my dependent variable in this case. My independent variable was the, let's say I go with the temperature, initial temperature, water temperature. Let's be precise here. It's the initial water temperature. And then I need to put all of the variables that I do want to control. So one of the variable would be the salinity of water. One of the variable might be the mass of powder. One of the variable may be the amount of water, volume of water. And one might be the order of the mixture. There's way more variables for this one. I would encourage you to continue finishing that fishbone. Now, let's have a look at the IUT for each of these. So let's start with the volume of snow. So the instrument might be your graduated cylinder. That would be the instrument. The unit here might be milliliters. And your technique here might be, once the snow has grown, I will gently level it and then read the volume of the graduated cylinder. That's important because it may not be leveled. It could be, it could have a curve. So you may want to shake it a little bit, but you need to shake it always the same way. So it's important to mention these things. Also, some students decide to do it in a certain container and then to transfer it to their graduated cylinder. If that's the case, they need to describe that. So let's do the control variable because it's always easier than doing our independent variable. So the mass of the powder will probably be a scale or electronic scale. The unit will probably be grams here. So I'm going to put G. And then the technique, I will use the scale to always include 5 grams of powder. So here, see, it's very important that you mention that students decide that, because if I have a students who say they'll be using 500 grams of powder, that's too much. It's wasting our resources. So it's okay for you to say, well, I do not approve this part of the experiment. I want you to have 5 grams. And that should be enough to come up with your answer. And then here, I do need to control the salinity of water. So here, I'm going to be... actually, in this case, I won't even be measuring the salt. I'll make sure that I have no salt in all of them. So what I'll just say here is I will use distilled water for all my tests. So that's, I don't even need to measure this. I would need to measure it if I was actually adding salt, but in this case, I'm not actually adding salt. So I'm just saying that I'm going to be using, I will use, oops, don't need to be in uppercase here. I will use distilled water for all my tests. Okay, good. So let's move on the order of the mixture. Let's say I will always add the water to the powder. I will always add the water to the powder and not the opposite. So you do need to define this. So not all variables will have an instrument in the unit, and that's okay. That's okay to recognize that. Okay, the volume of water, I'm going to be using a graduated cylinder again. Perfect. In this case, I'm going to be using milliliters again. So let me use this here, milliliters. And then I need to say how much. So maybe I'll say I will add 100 milliliters of water to each test. And then students could describe a little bit how they're going to read the value on the graduated cylinder. They could be more precise also and say, I'm going to be using 100 mil graduated cylinder or 150 mils and then measure 100 from it. So they need to describe what they're going to be doing. They need to show that they thought about how they will perform this experiment in the lab. Keep in mind that when I say lab, I have a very broad definition of what I mean by a lab. Now, the last part is my independent variable. This is the one that takes a little bit more time. This is the initial temperature. So, in this case, I'll probably be using a thermometer. I'll probably be using Celsius as my unit. But if I was using Kelvin or Fahrenheit, I would need to mention it here. And then I need to give my increment. So let's say I will start at 20, which will be my, baseline. And then I'll try temperatures that are less than 20 and more than 20. So I can say I will use the thermometer to and the hot and cold water from the tap to get the following temperatures. So 10 Celsius, 20, 30, 40, 50, etc. If I plan on using a hot plate or a kettle or even using the fridge or the freezer, I would need to mention that here. So with the independent variable, there's always some sort of an increment because you are changing something. So this is how we use the fishbone. So the fishbone is one of the very useful tools to show that students are ready to go in the lab. The next part is also to create their table where they will record their results. And we've created at Smarter Science this template that you can use with any science experiment. That includes the two variables, the independent and independent variable. And the great thing is that it is using this orange or the purple and the green that continues from the previous poster. So let me go in Microsoft Word and we're going to try to use it. So let me open it in Microsoft Word. Here we go. So there's Microsoft Word, and I'm going to select my independent variable. So let's say I'm doing here the penguin. So my independent variable was the surface area of the wings. Okay. So, and in this case, it's centimeters square. Let me put this as a square. So I have to include what my measuring units will be here. So centimeters square. And then I have to put my dependent variable. And this was the duration of the flight. And that was in seconds. So I'm going to write that it is in seconds. Okay, so now I've written my variable here. Now, my control group in this case was 0. And I don't need to repeat my units because I have it here. So that's no wings, basically, 0 centimeter. And then I had 10, 20, 30. If your students have more conditions, they can just add rows. So they would have a fourth and a fifth conditions. So that's how you change the independent variable. Now, the dependent, that's something that you will measure during the experiment. So as part of the preparation, you would prepare this, and then you would take this to the lab, and you would start to collect data. Now, depending on the grade level, with younger grades, we do suggest that they get at least 3 measurements. So they repeat the experiment at 0, so no wings, 3 times, and measure the time. And then they create wings that measure 10 centimeters square, and then they repeat this experiment 3 times for this, and then at 20, and then at 30. With older students, it would be better if they repeat it more. Like you can go all the way to 10. And when it involves humans and plants, And again, if it involves humans or animals, make sure that you have it vetted by your regional science fair ethics coordinator. But you would need probably, like with plants, you would need way more than 10 measurements just to validate the results. And at the end, the students would use the average. This is when we are more in the orange column of our Smarter Science poster, when you start to analyze the data, because you're not interested in all of these data points. You're interested mostly in the average. Could be the mean or the median, depending on what you're trying to accomplish here. So this one is usable with anything. See, if I use the same one for the instant snow experiment, the same template, in this case, my independent variables was the water temperature, the initial water temperature, okay, which was in Celsius. And my temperature for my control group was 20, room temperature, but I also had 10, which was colder than room temperature. I had 30 and 40. So your baseline is always like what is considered like normal. So a temperature of 20. Some students may say, oh, the baseline will be 0 because it is ice. But usually for temperature, we would consider room temperature to be the baseline, and then you either make it colder or warmer. And then in this case, it was the volume of snow the volume was in milliliters. And now we would start the experiment. So I would make snow using all of the variables that I've controlled at 20 degrees Celsius, and I would take 3 measurements and then calculate the average. Then I would do it with water at 10 degrees Celsius, take 3 measurements, calculate the average. So again, no matter what kind of experiment you're doing, using this table to collect the results is a great way to record all of the data, so you can use always the same template with the students. Now that we've seen all the tools that you can use to help your students doing a science experiment type of project, now we're going to look at invention and innovation. And to do that, students will use the engineering design process. So I do have a French version here on the screen, but it has so many pictures you should be able to follow. So when students are trying to solve a problem using the engineering design process, the first thing they need to do is to understand the context, see what's happening. And this is where they should be using tools like an interview or a survey or observing using a phone or something. So let's say they want to help, in this case, in this picture, they want to help the principal. So they want to help the principal, so they are interviewing the principal about the problem with garbage in the schoolyard. So that's the problem they've decided to target. They have a conversation, they take observation, they do a recording, just so that they can collect data about the situation to better understand the context. This is also where students should have empathy, because invention and innovation projects are all about empathy. They're all about helping someone and trying to see how that person feels to better support them. The second step would be to define the problem. So once you have the interview, you collected data, you collected observation, maybe a survey, you look at all of this and you try to define what exactly is the problem. So in this case, it is causing back injury to the custodian because all of the garbage is on the ground. So he always has to to get down to get the garbage. So that is their definition of the problem. Then they get into this loop, and this is called iteration when you work with the engineering design process, where you come up with ideas. So in the first part, then you build a prototype, and then you test it. And this loop will continue over and over again until you have an invention that works well. I was going to say to work perfectly. It's never perfect, but at least it will do its job, the job intended. So as the students test the prototype, they may realize, oh, okay, it is collecting certain type of garbage, but really has a hard time collecting this type of garbage. So I need a new idea. So in this case, this little scenario, the students are using a robot to help the custodian collect all the garbage in the schoolyard. So they come up with new ideas, they build a new prototype, they test it, they realize they need to change it, so they bring new ideas, assemble a new prototype, and then test it. Once they have the final products, this is where they will build their final design. So this is happening at the step here where they actually create the final invention and then they present it to the person that they want to help. Keep in mind that it can be a person, it could be society, it could be community, it could be a group of persons, it could be an animal, it could be all of these things. As much as possible, also, you want to involve that person or that group of person in the process. So even though you had the initial interview, as you're going through the iteration, you may want to talk to that person to get more feedback about the different iteration that you are doing. So this is the engineering design process or the technological problem solving process. Two different names for the same thing. Now, one of the strategy that we suggest that students use when they have to come up with ideas, because it's not easy to ask students like come up with an invention, is to use what we call Scamper. And Scamper is a list of questions that they use to look at an object. And it could be a very simple object such as, let's say, a paperclip. So they look at a paperclip like this, and they use Scamper to try to improve this paperclip. Or it could be a pencil sharpener, or it could be the mouse on their computer, or it could be anything. So they look at an object or a service or a system, and then they try to improve it. So the first thing that they're going to ask as a question is, what can I substitute? What part of this object could I substitute with something else? And substitution happens all the time. Like, can I substitute, let's imagine the old school trackballs. Now they've substituted the ball with a little light that will track the motion of the mouse. So is there anything on the object that I could substitute with something different? The next word is combine. And then they have to brainstorm. And this is usually happening in a group. We rarely brainstorm ideas by ourselves. And what I always tell students is when they use Scamper, there's no stupid idea. Maybe it is stupid, but stating a stupid idea that we get from one of the questions will actually trigger other ideas around the table. So even if something seems like it wouldn't work or it's a little bit ridiculous or silly, I will still say it because it brings new idea around the table and may start a super awesome, amazing, ingenious idea with someone else. Then you have combine. Can I combine this object with another one? Could I take my keyboard and my mouse and combine them? It happened in the past. Someone combined the eraser and the pencil. Or in 2007, when Steve Jobs went on stage and said, hey, today I'm going to be presenting an internet device, a phone, a music player, a camera. And he says, no, you're not getting what I'm saying. I'm presenting only one device. So he had combined all of these devices together. A spork, a spoon fork would be another example of combining. So your students has the object, let's say the pencil sharpener, and they go, what could I combine with the pencil sharpener? Next one is adapt. Can I find other use for the same product? I look at my paperclip. Can I find other use for the paperclip? Can a paperclip be used for something else? Next one is magnify and minify. So the students have to imagine that the object is way bigger or the object is way smaller. So let's say I'm doing the paperclip. Would there be a use for a giant 1 meter paperclip or for a tiny one that would be like 5 millimeters? If I do the tea bag, I could Scamper a tea bag. Would there be a use for a giant tea bag or a tiny tea bag? And using Scamper is a lot about having mental images. So students should shut their eyes and start to picture those things. The next word in Scamper is produce. What happened if I change the shape, the material? Let's say my mouse here is made of plastic. Would there be an advantage of having a wooden mouse? A mouse made of glass, a mouse made of fabric. So they have to think of these things. What happens if I change the shape? So instead of being rounded, it's square or rectangle or triangle. Um, Try to think about these things. Now there's eliminate. Is there any part of my objects that are not necessary? And this happened with the actual phone. Remember, in 2007, BlackBerry was the biggest brand for a cell phone, and it had a keyboard, a physical keyboard. And Apple says, like, let's get rid of the keyboard. So they decided to eliminate. If you look at remote controls from the 80s and the 90s versus the one we have, they got rid of most of the buttons. So they eliminate. If I look at my tea bag, would there be a reason to eliminate the little string or the little piece of paper? What can I eliminate? Again, not all words will lead, or all questions will lead to an invention or a smart idea, and that's okay. Then there's reverse. What happens if I use this backward? The up becomes down and down becomes up, or left becomes right and right becomes left, or if I do it in the opposite direction. What happens if my mouse works like this instead of like this? Would there be a use for that? What if I reverse my keyboard? I have the numeric keypad on the left and I have the regular keyboard on the right. Would there be a use for that? So just try to think, and sometimes students will go, whoa, that's a smart idea. I could use this. So I encourage you to use Scamper when students are stuck. They can't find ideas and they need, as part of the engineering design process here, they need to come up with ideas. Scamper is a great way to do it. And as I said, it's pretty rare that students will come up with an invention that didn't exist at all before. Most of the invention are actually based on an existing product or service that is being modified. So Scamper is a great tool to use with your students. And the last part would be to communicate your science fair project. So now we had a look at the engineering design process for innovation and invention. We look at all the tools to come up with a proper science experiment. Now we need to communicate. You will find on the Youth Science Canada website a project entry guide that explains how the students could describe their project and write their report. And you can also go on that website to come up with some ideas from previous year. So let me just show you here. I'm going to load a browser window right here. So give me 1 second. I'm going to do that. It's going to load. And I encourage you, let's put this full screen, to go to projectboard.world/YSC. projectboard.world/YSC, and it's going to bring you to the virtual Canada-wide Science Fair, keeping in mind that in 2021, 2022, it was a virtual event. So I'm going to go here on Canada-wide Science Fair 2022, and you will find, you remember those challenges? You can see some of the projects here that were presented in the past. So you can say, I want to see all the projects in digital technology, and you're going to have an idea what they look like. Now, as you look here, you will see that this is the different sections that we recommend for the report. Why, how, what, so what, what's next, the references, and a video. So the why. Why did you do this project? How did you do it? So that's your procedure, your method. What happened? What kind of results did you get? So what? What kind of conclusion can you come up from this project? And what's next? If you had more time to push this project further, what would it be? And then your references. So I encourage you to have a look at some of these projects. You will see some medals on some of them, like this one. You could see that this project received different medals at the Canada-wide Science Fair. So it gives you an idea and gives your students some ideas about the kind of project that we see at the Science Fair. So see, like these ones, this is a gold medal. It's called Waterworks. And we have the why, the how, the what, the so what, and the what's next. And if I go, let's say, under the how, I have a description of how the students created this project. And I can even look at their slides. So in this case, it is an innovation. So the students created something. So I hope that helped you. I hope that you want to learn more about the Canada-wide Science Fair and the Quebec Indigenous Science Fair. Thank you so much for spending time completing this workshop, this self-guided workshop. If you have any questions, feel free to contact the team at the Indigenous Quebec Science Fair. They will gladly answer all your questions. Thank you. Bye-bye.